Hello and welcome to the Week 9 Math 2419 review. In this review, we'll be going over tangent planes and normal lines, then we'll get into some extrema of multivariable functions, and lastly talk about Lagrange multipliers. Let's go ahead and get started with tangent planes and normal lines. All right. So we'll start with the definition of a tangent plane and a normal line. Let's say we have a surface, and the surface is described by a function f of x, y, and z equals to 0. So this can be thought of as being a level surface. So we have a function of 3 variables, and we're setting it equal to 0. And wherever that is true, that's our surface. Well, then we can take the gradient of this surface, and it'll give us a vector that's normal to the surface. But of course, if our gradient vector is equal to 0, it doesn't really describe a vector that points anywhere, so we specify that gradient of f is a vector normal to the surface whenever our gradient is not equal to 0. So whenever it gives us an actual vector that points somewhere, it's always going to be normal to our surface. And if you recall from earlier in the course, we can use a normal vector to define a tangent plane. So a big takeaway is that the gradient of a surface is a normal vector to that surface. So we'll start off with an example. Let's say you have the level surface 4x squared plus 3xyz is equal to 0, and you want to find a normal line and a tangent plane at the point -1 to -1. Well, first off, we can find our normal line by finding a normal vector. Do that by taking the gradient. The gradient would be the derivative with respect to x is 8x plus 3yz. The derivative with respect to y is 3xc, and the derivative with respect to z is 3xy. So that would be our gradient, and then we can calculate the gradient at our specific point, -1 to -1, and that gives us the vector -14, 3, -6. Well, here we have a point and a vector, and that is enough to define a line. So we can say that our normal line is the line defined by our normal vector, -14, 3, -6, times some parameter t, and then we just add our initial point, -1 to -1. And this will give us a line passing through our point that is normal to our surface. We can also use this normal vector to define a tangent plane. If you recall, we can take our vector, so to define our tangent plane, we simply take our normal vector, -14, 3, -6, and take the dot product with x plus 1, y minus 2, z plus 1. Set that equal to 0. Now this plus 1, minus 2, and plus 1 here, I actually got from this initial point. I simply took a general x, y, and z coordinate and subtracted our initial point from it. So x minus -1 becomes x plus 1, y minus 2 stays y minus 2, and then z minus -1 gives us z plus 1. Now, if we take this dot product, we get -14x minus 14 plus 3y minus 6 minus 6z minus 6 equals to 0. And we can, of course, rewrite that -14x plus 3y minus 6z is equal to 26. And this could be our final answer. Actually, it is our final answer, so we'll just leave it like that. This would be the equation for our tangent plane, and this would give us our tangent line. Perfect. All right. So go ahead and work out this practice problem. Again, it's going to be the same kind of setup as the previous one. Find a normal line and a tangent plane. Given the equation y e to the x plus x squared is equal to 1 at the point 1, 1, 2. And I'll give you a couple of minutes to work that out on your own. Go ahead and go through this. First off, one thing to note is that in order to take a level surface, we need to make sure that our function is equivalent to 0. So our first step should be moving everything over to the one side. In this case, it doesn't really matter since when we take our gradient, which is our second step, this 1, since it's a constant, will just disappear. But if instead this had been like an x or some function of x, y, or z, it would have made a difference. Regardless, our gradient comes out to be z squared. Oh, forgot my x, forgot my first term. It would be y e to the x plus z squared e to the x, and then 2xz as our gradient. That would be the derivatives with respect to x, then y, and then z. And then we know that this is normal to our surface at every point where it's not equal to 0. So we can find our normal vector by taking the gradient at the point 1, 1, 2. And that gives us the vector e plus 4, comma e, comma 4. All right. Cool, cool. Um, Oops, I am
What class is this for?
sorry, what is this?
Yeah, what class is this for?
This is for Math 2419.
2419?
Yes, that's correct. All right. Cool, cool. And as I was saying just a moment ago, I realized I made a slight mistake. 0.112 in order to be this one right here. That should have been the point, that should have been e plus 4, just like that, in order to be on our surface. Doesn't really make much of a difference in our overall problem, but if you'll recall, what we were doing is we had a level surface, and we were trying to find a normal line and a tangent plane to it. And in order to do that, we took the gradient at the point 112 in order to find the normal line at the point 112. From here, we can actually write the equation of our line by simply taking our normal vector, adding our initial point. We can also write our tangent plane, again, by taking the dot product between our normal line, e plus 4, e 4, and x minus 1, y minus 1, z minus 2. And of course, this is basically just the vector x, y, z subtract your initial point. And set that equal to 0. And what we get is that our equation of our tangent plane comes out to be e plus 4 times x plus e times y plus 4z is equal to 2e plus 12. I did the last couple of steps all in one go, where I basically moved all of my non-variable terms, all my constant terms over to the right-hand side. That would be your final answer. All right. And that's fairly straightforward for how to solve for tangent planes and normal lines. Any questions?
No.
All right. In that case, we'll go ahead and move on to extrema of multivariable functions.
What days do you have these classes on?
Um, these weekly reviews are every Monday at 2 o'clock.
Is it always on Calc 2?
Yes, we do offer other classes. Is there a particular class you're interested in?
I'm taking PRE 2260. It's a stats class, and then I'm also taking linear algebra.
Okay.
Yeah.
If you give me a moment, I can send you a link that might be helpful. Let's see.
I mean, I'll be taking this in the future.
Right.
But yeah.
Let's see. go. So I know that our website has all of the weekly review schedules. I'm just trying to find where exactly those the weekly review schedule is so that I can send it to you. We also offer drop-in tutoring. I don't know if you're familiar with how that works. But
Yeah, I
here's
do use the service, but yeah, it's just for OPRE 3360, there is no drop-in tutoring available.
right. Is OPRE? I'm not sure. The Computer Science Mentor Center might help with that though, since I believe it's more of a. Is it a computer science stats class?
Oh, it's a no, it's not.
Okay. Then yeah, if it's not supported, there's not a whole lot we can do. We do offer support for 2418 though. Linear algebra we do support.
Yeah. Okay, so can you move on with the problem, or like
Sure.
go with work on the problem?
Um, yeah, I will just continue on with the weekly review. All right. So for extrema of multivariable functions, there is one main theorem that we use to essentially determine whether or not a function has an extrema. That is called the extreme value theorem. And the extreme value theorem, we'll give the very mathy definition first, and it says if f is a continuous function on a closed and bounded interval, bounded region, then there is at least one max and one min. It doesn't say that there is exactly one, but at least one. And basically, in more plain terms, if you have a function, some kind of graph, let's say like this, and you put a fence around it so that you're looking at just one specific area of that function, well, we also say this function is continuous. So it doesn't go to infinity, it doesn't go to negative infinity, and it doesn't jump around. Well, then we say that there's at least one point where it has to be highest and one point where it would have to be lowest. And in this case, the lowest point would be right about on that boundary point. So basically all it's saying is if you have a function that's not infinite in any direction, so not infinite up or down, and it's not infinite in like its size, so we're looking at just a finite section of it. In this case, we put these boundaries right here and right here. Then it's going to hit a tallest point and a shortest point. And this is true for not just two-dimensional graphs, but also three-dimensional ones. You can think of it as being like the height of water in like a swimming pool. There'll be little waves going around inside of it, but there's going to be a point where the water is the highest and a point where the water is at the lowest. Because you know that it's a closed and bounded region with a continuous water surface. All right. And likewise, in one dimension, we had the definition of what's called a critical point. If you'll remember, in two dimensions, for just functions of one variable, a critical point was where f the first derivative f prime of x was equal to 0? Well, in higher dimensions, it can be 3 dimensions, it can be more. We say that a critical point occurs wherever the gradient of f is equal to 0 or the gradient is undefined. And that is one part of the definition in 2 dimensions that I forgot. Your first derivative can be equal to 0. So pretty much the same definition, except in this case we're looking at the gradient rather than just the simple. And please note that in higher dimensions, in this class at least, you'll usually see something like f of x, y is equal to z, and you'll just be using gradient of f is equal to f sub x, comma f sub y. Sorry, that should be a pointy bracket, like that. And just like in 2-dimensional graphs with functions of one variable, your critical points are potential maximums and potential minimums. So let's go ahead and find and classify. Go ahead and just find critical points. Of the function f of xy is equal to x squared y plus 3x cubed minus y. Well, then clearly our gradient would be the derivative with respect to x, so 2xy plus 9x squared. And then the derivative with respect to y is x squared minus 1. In order to find our critical points, we set this equal to 0, since clearly it's going to be defined everywhere, since 2xy plus 9x squared is continuous and so is x squared minus 1. So we need to solve this system of 2 equations. 2xy plus 9x squared is equal to 0, and also x squared minus 1 is equal to 0. I'm going to start by trying to solve this second equation because it only has one variable, so it should be easier, and it tells me that x would have to equal -1 or x would have to equal +1. So using this, I can say if I plug x is equal to -1 into my first equation, I get that -2y plus 9 has to equal 0, and that tells me that y is equal to 9/2. So that would give me a first critical point because I used my x value of -1. The corresponding y value is 9/2. This is my first critical point. For my second critical point, I plug x is equal to +1 into this equation, 2xy plus 9x squared equals to 0. And I get that +2y plus 9 is equal to 0. So y is equal to -9/2. We get our second critical point of +1, -9/2. But how do you tell if this is a max or a minimum? Well, in this, we are not entirely sure using just what we know. We need something else, and that something else is the second derivative test. So here's the second derivative test. Let's say you have this number d, and we're going to define it by saying it's the second derivative with respect to x times the second derivative with respect to y minus the derivative with respect to x then y squared. Well then, we can say if this value d is bigger than 0 and your second derivative with respect to x is also bigger than 0, then we have a relative minimum. if d is bigger than 0 and your first derivative is smaller than 0, we have a relative max. If your d value is smaller than 0, we have what's called a saddle point. And finally, if d is equal to 0, the test is inconclusive. All right, so let's try and use the second derivative test to evaluate these two critical points that we found right here. So we know that our second derivative with respect to x of our initial function, I'm going to try and work it out over here, something like that, get f sub xx is equal to 2y plus 18x. We get a second derivative with respect to y of exactly 0, and f sub xy is equal to positive 2x. Well, if we plug in, then we can define d to be equal to, since f sub xx times f sub yy, since f sub yy is 0, that would be 0 minus f sub xy is 2x squared gives us minus 4x squared. Well, for any value of x that's not equal to 0, d is going to be smaller than 0. For example, with this first critical point, plug in x equals negative 1, we get negative 4 times 1, so d is equal to negative 4, which is smaller than 0. Since d is smaller than 0, we get a saddle point. And similarly, for our second point, we plug in 1, we get d is equal to negative 4. That's smaller than 0, again, a saddle point. And you might be wondering, well, what is this saddle point? What does it mean in terms of a graph? If you'll give me just a second, I can pull up a graph of it. And t is equal to squared y plus 3x cubed minus y. Okay. All right. And I will share this graph in just a second. All right. Perfect. So you can kind of see this graph right here. If we plot our point negative 1 comma 9 halves, then the corresponding z value would be 9 halves minus 3 minus 9 halves, so we get we probably want the other point. So we'll go ahead and plot down the other point. 1 negative 9 halves positive 3. So this point right here, this tiny dot, is actually one of our saddle points. And if we scrolled out just a bit, you could see how in one direction, we actually have a minimum, like swooping down and then coming back up. But in a second direction, the x direction, we actually have what's kind of like a maximum. How it goes up like that and then comes down. So that's basically what a saddle point looks like. It's a minimum in one direction and a maximum in another. So it's kind of not really a true maximum or a true minimum. A true maximum would look like more like the top of a mountain, maybe less spiky, but there would be like an actual peak, and a true minimum would be like the bottom of a bowl where there's an actual point and all points above it are higher than it. So yes, both the points in this case turned out to be saddle points. You'll notice that we don't actually have a maximum or a minimum. And you might be thinking, well, wait, that's not allowed because of the extreme value theorem that you talked about earlier. Well, in this case, it actually is allowed because we're looking at the function over the whole xy plane. So since it's the whole xy plane, we say that it's not a closed and bounded region. It's completely open. It goes on forever. So the extreme value theorem does not apply here because we're looking at an infinite plane. We'll talk a bit more about the extreme value theorem in a bit. But for now, I would like to give a practice problem. So go ahead and find, find and classify using the second derivative test the critical points of f of xy is equal to e to the x squared minus y squared. And I will give you a couple of minutes to work on that. All right, let's go ahead and go over this. So start by finding the gradient of this function, and we get that the gradient would be 2x e to the x squared minus y squared, comma, negative 2y e to the x squared minus y squared. And for convenience, I'm actually just going to factor out a common term. I noticed that e to the x squared minus y squared is in both. So I get e to the x squared minus y squared. I could have also factored out a 2, but I've already started doing my factoring, so I'll just leave it like this. And critical points occur where this gradient is equal to 0. Well, clearly, e to any power is always going to be bigger than 0, so we can actually ignore this whole first term. And then we just need to solve the system of equations 2x is equal to 0, and negative 2y is equal to 0. And clearly, this only is satisfied at the point 0, 0. So this would be our only critical point. Next, we need to classify it, and to do that, we need to find f sub xx, which is, in this case, we need to use the product rule since our x derivative is 2x e to the x squared minus y squared. We get 2e to the x squared minus y squared plus 4x squared e to the x squared minus y squared as our x derivative. Similarly, for our y derivative, we get negative 2e to the x squared minus y squared. This time we have plus, checking, yes, plus 4y squared e to the x squared minus y squared as our y derivative. And finally, we have f sub xy, and for that we get a derivative of minus 4xy e to the, I'm correct, yes, minus 4xy e to the x squared minus y squared. Now, we could write out d in terms of all of these, but we can also write that d is f sub xx, f sub yy minus f sub xy squared. So at our critical point, 0, 0, we can say f sub xx would be, since x is equal to 0, the second term goes to 0. Our first term is 2e to the 0th is 2. Our y term would give us negative 2, and our z term would give us 0. So at our critical point, our d value is negative 4. Because this is less than 0, it tells us it is a saddle point. Cool. And it was just a coincidence that all the critical points in my problems turned out to be saddle points. It a lot of times depends on the problem that you get. We'll see maximums and minimums fairly regularly as well. All right. Cool. Let's go ahead and move on to the third topic. And this is Lagrange multipliers. So if you remember all the way back in finding maximums and minimums of functions of one variable, sometimes the question would be phrased like find the maximum and minimum value of f of x on the interval from like 0 to 10 or something. And there would be two things you would need to check for. First, you need to check the critical points, the places where the first derivative was equal to 0. But then you would also need to check the endpoints. Because you would need to make sure that f of 0 wasn't a max or min and f of 10 wasn't a max or min. So we have to do something similar when we're looking at functions of multiple variables. But with functions of multiple variables, rather than having just two endpoints, we might have like a whole boundary. For example, we could say, what's the max or the min of a two-dimensional function f of x and y is equal to 2x cubed plus y to the fourth on or inside the disk x squared plus y squared is less than or equal to 1. Well, in that case, our boundary isn't just 2 points, it's a whole circle. We'd have all kinds of points, and we can't just plug in all the points because there's an infinite number of points. So how do we evaluate these endpoints? And the answer is using Lagrange multipliers. And Lagrange multiplier is, well, we'll go ahead and give a formal definition. So let's say f of xy is the function that we're interested in. I'm saying the function we're interested in because that's basically what it is. It's the one we're looking to maximize or minimize. And let's say we have another function. Be a constraining function. G of xy is a constraining function. So in the above example, f of xy would be this 2x cubed plus y to the fourth, since that's what we're trying to find the maximums and minimums of. Our constraining function, g of xy, would be x squared plus y squared minus 1 is equal to 0. Because it comes from this constraint that we have to be inside this disk. Then we can say that critical points also occur whenever the gradient of f is equal to some constant lambda times the gradient of g. And lambda can be any real number. So basically any constant. And note that you may still need to find, you also need to check the normal points, the normal critical points that occur where the gradient of f is equal to 0. That is also important to check. Okay, so let's go ahead and do the example that I wrote out right above, and that was find maximum of f of xy is equal to 2x cubed plus y to the fourth on the disk x squared plus y squared is less than or equal to 1. Okay. Well, first off, we need to find our gradient of f, and that is 6x squared 4y cubed. And we still need to find our normal critical points. So we set gradient of f equal to 0, and we can clearly see that that would only occur at the point 0, 0. That should be a point, so I don't know why I'm writing the brackets. This would be our first critical point, 0, 0. Well, second, we also need to set this gradient of f, 6x squared 4y cubed, equal to lambda times the gradient of g. The gradient of g would be the gradient of this constraining equation, so 2x comma 2y. And this gives us a system of equations. Here we have 6x squared is equal to 2 lambda x, and 4y cubed is equal to 2 lambda y. Now, solving this is a bit weird because this is one of the times when you actually have to be super careful about not dividing by 0. So in this case, we can say, well, we could cancel our x's from each side of our first equation, but only if x is not equal to 0. So we can say either x is equal to 0, because if x were equal to 0, then this first equation would of course be satisfied. Or we can divide both sides by 2x and get that lambda would be equivalent to 3x. And if lambda is equivalent to 3x, well, actually, we'll get to that in a sec. So it's almost like we start making this little tree. So if we start out with 6x squared is equal to 2 lambda x, we can do the first thing, which is x is equal to 0. Well, then if x is equal to 0, we want to look back at our constraining equation and say then, well, 0 squared plus 1 plus y squared has to equal 1. We're ignoring the smaller than or equal to part because we're only concerned with the exact boundary, and that tells us that y is plus or minus 1. So this would give us two critical points, 0, negative 1, and 0, positive 1. Our other option is saying, hey, maybe lambda is equal to 3x. In that case, we plug our lambda into our second equation, and we get that 4y cubed is, of course, equal to 2 times 3x times y. 2 times 3x times y, and that gives us 6xy. From here, we can say, okay, if we divide both sides by y, we're assuming that y is not equal to 0, and we would get that, well, x would then be equal to 4 over 6 is 2 over 3 y cubed. If y is equal to 0, then we can plug that into x squared plus 0 squared is equal to 1, and we would get the critical point negative 1, comma 0, and positive 1, comma 0. If x is equal to 2/3 y cubed, that should be a y squared, sorry. Okay, yeah, so these questions tend to get a bit complicated in solving your various systems, but you can kind of see what happens. Instead of plugging in x is equal to 2/3 y squared, I'm actually going to write it as 3/2 x is equal to y squared, because then I can substitute it into my equation x squared plus y squared equals to 1 and get x squared plus 3/2 x is equal to 1. If I solve this x squared plus 3/2 x is equal to 1, I'm just going to rewrite it like x squared plus 3/2 x minus 1 is equal to 0. Solve it using the quadratic equation. Well, then from there, I get that x is either equal to negative 2 or x is equal to positive 1/2. And because I know that 3/2 x is equal to y squared, I can then use it to solve for y and say if x is equal to negative 2, then 3/2 times negative 2 is equal to y squared. So then y is equal to, in this case, because this is negative, I would have the square root of negative 3. Since that's an imaginary number, we can't do that. So we have no critical points. But then if x is equal to positive 1/2, then we can have that 3/2 times positive 1/2 is equal to y squared. So y is equal to the square root of 3 over 4. Because we're taking the square root, we actually need to consider both the positive and the negative cases. So then that would give us two critical points, 1/2 negative root 3 over 4, and also 1/2 positive root 3 over 4. Cool. Okay. Am I missing any critical points? I don't believe so. Then we would actually need to work through the same process using this second equation. Say, well, either y is equal to 0 or lambda is equal to 2y squared. And then we would have to work through that whole process again. I can do it very quickly, I suppose. So we have 4y cubed is equal to 2 lambda y. If we take y is equal to 0, well then we've already actually found our critical points right here. So we can just say done. If lambda is instead equal to 2y squared, then we would get the equation, plugging it in, we get that 6x squared is equal to 4y squared x. So then either x is equal to 0, and again, we found the critical point, so we're done. Or we can say that 6 over 4x is equal to y squared, and again, this simplifies down to 3/2 x. And we can actually see we've already done it there as well. So that wasn't actually too bad. But regardless, we can now find all of our critical points. I'll just go ahead and highlight them. Way back at the beginning, we found 0, 0 as a critical point using gradient of f is equal to 0. We also found 0, -1, and 0, +1. We also found -1, 0, and +1, 0. And then we found these two slightly weirder ones. And I will go ahead and write all of those right off here. 0, 0, -1, 0, +1, 0, 0, -1, 0, +1, 1/2 negative square root 3 over 4, and 1/2 positive square root 3 over 4. And when we plug in our function values at all of these points, i.e. we just evaluate f at that point, remember our original function was this 2x cubed plus y to the 4th. Then we can see precisely what these function values are. F of 0, 0 gives us 0. F of 0, 1 gives us 1. F of 0, -1 gives us 1 as well. F of -1, 0 actually gives us -2, and f of 1, 0 gives us +2. And then when we plug in these last two, we would get 1/2 cubed is 1/8 times 2 is 1/4, plus the square root of 3 over 4 to the 4th, and it won't matter if it's positive or negative square root because it's being raised to the 4th power anyway, it'll end up being positive. That comes out as being 9 over 16 plus 1/4, which is about equal to 13 over 16, I believe. And here we can clearly see the -2 is the minimum value and the +2 is the maximum value. So that would be our final result. And it can get fairly messy, but if you stay organized, you'll end up getting the right result. All right, one practice problem for you. Find the maximums and minimums of f of x, y, z is equal to y squared minus 10z on the constraint, given the constraint that x squared plus y squared plus z squared is less than or equal to 36. And I will give you a couple of minutes to work that out. All right, let's go ahead and go over this problem. It is considerably simpler than the last one, so hopefully it wasn't too difficult. First off, we need to take the gradient of f, and when we do that, clearly our x derivative is 0. We get 2y and then negative 10 as our third component. And if you actually think about this, you can see that our gradient is actually never going to be equal to 0 because this third component, the negative 10 in the z space, is never going to equal 0. So our gradient can never be equal to 0. So we have no critical critical points coming from the gradient of f being equal to 0. Next, we need to calculate the gradient of our constraint function, and that would give us 2x, 2y, and 2z. So here we can go ahead and set up our equation that says gradient of f is equal to lambda gradient g. We get that 0 is equal to lambda times 2x. We also get that 2y is equal to 2 lambda y, and negative 10 is equal to 2 lambda z. Now, looking at this first equation, we get that either x is equal to 0 or lambda is equal to 0. Of course, if you actually look a little deeper though at our third equation, you can see that if lambda would equal to 0, then we would get that negative 10 is equal to 0, and that's not true. So lambda can actually never be equal to 0. So our first equation just tells us our x value has to be equal to 0. All right, then we look at our second equation, and this tells us, well, either y is equal to 0 or lambda is equal to 1. Let's go ahead and kind of write out our tree again. First off, if we have y is equal to 0, well, since we already know that x is equal to 0, we can take these x and y values and plug them into our constraining function. So 0 squared plus 0 squared plus z squared has to equal 36. So then z is plus or minus 6. And we get two critical points, 0, 0, negative 6, 0, 0, positive 6. Next, if lambda is equal to 1, well then negative 10 is 2 times 1 times z, so z would equal negative 5, and that's a second critical point. Sorry, not quite yet. If z is equal to 5, then we have an x value and a z value, so we can again write, using our constraining function, 0 squared plus y squared plus negative 5 squared is equal to 36. So y squared is equal to 11, and that gives us two critical points. 0 square root negative 11, negative 5, and 0 positive square root 11, negative 5. Cool. And finally, to solve this third equation, well, we could solve it and say that lambda is equal to, let's see, that would give us that lambda is equal to negative 5 over z. You could plug that into our second equation and get that 2y is equal to negative 10y over z, or that would give us the equation y equals equal to 0, which we've already solved, or basically z is equal to negative 5 again, which we've already solved as well. So we can say that we're actually done from this point. And we've actually only found really 4 critical points. This one, this one, this one, and this one. So we can evaluate f of 0, 0, negative 6, f of 0, 0, positive 6, f of 0, negative square root 11, negative 5, and f of 0, positive square root 11, negative 5. And then evaluating those 4 points, we would get for negative 6, 60, and f of 0, 0, positive 6, we actually get negative 60. F of 0, negative square root 11, negative 51, we actually get 61. And the same for our final. So we can see that 0, 0, positive 6 is actually a minimum. I should say MIN, minimum. And the other two critical points are maximums, and our first point is neither. So there you have it. That is solving for Lagrange multipliers. There is another way you can solve for Lagrange multipliers that involves parametrizing your boundary, but we don't really have a ton of time for that. And I personally just prefer finding wherever the gradient of f is equal to the lambda gradient g. Right. That's all for today. Hopefully you've understood the concepts, and best of luck. Thanks for watching.